Next speaker, Yauhen Baranouski. Yauhen, good luck and let's go.
Okay, so let me introduce myself a little bit. So I'm a lead software engineer at EPAM, more than 10 years of practical experience in different domains, including e-commerce, trailing, and statistics, hands-on engineering and architecture practice in Java, cloud, data, and NoSQL. And at spare time, I experiment with knowledge management and enjoy video games. So let's dive into our agenda. It's pretty simple, but pretty packed. The first part will be a small warm-up about honorable mentions, small changes that are noteworthy nevertheless. It's about the performance changes in Java, which Java has been pursuing quite aggressively recently to catch up with computational trends of AI and ML. And the third part will be some sort of outro with more traditional adjustments in core APIs, etc. And as much as possible, I tried to support all the theory with some practical examples, which you will find in my public GitHub repository. So let's dive into it. The first warm-up will start with some security changes. First of all, it's about PEM format support. Many security-related tools like OpenSSL, but historically Java didn't support it very well. It was necessary to write a lot of boilerplate code in order to work with that. But now the situation has changed, and here you can see quite a concise sample of code how to do that with core APIs. The second GEP is about security as well. It's about the ability to derive additional case from general use cases. For example, to simplify GDK internals, to standardize them more, to expand GDK out-of-box security APIs, and to allow third-party contributors to provide custom implementations as well. So that feature was in preview previously, and now it's finalized in GDK 25. The next GP is about some code cleanup in GDK itself. So they dropped support for 32-bit x86 port because it wasn't used a lot and just obfuscated the code base of GDK itself. And a little bonus, it's GP associated with it, but nevertheless, it's our beloved string class, and it has some small but pleasant improvements in hash code implementation performance, which is nice to see. So now so why doesn't switch? Here we go. So the next part is about GVM and performance changes. And first of all, I'd like to mention that I tried to run some benchmarks. Here you can see my configuration, just in case you want to compare or run it yourself. And as for the GDK distribution choice, I chose Zulu 24 and 25 because by default, more widespread distributions like Oracle GDK do not include all the garbage collector options. And here we would like to experiment with Shenandoah. And Zulu includes it out of box. And the first feature to talk about here is about AOT optimization. So that's about ahead of time optimizations. GDK 24 introduced the ability to reuse the metadata that is compiled from class files at runtime and reuse that in the form of a cache for subsequent runs of your application to boost the startup time. And now the CLI ergonomics of that feature has improved. Previously, you had to explicitly perform 3 steps. Namely, you had to collect the configuration, which listed all the class files you would like to process. Then you had to capture that list as a cache, and only then you were able to actually use the cache. Now it's just 2 steps. So basically, the first 2 steps collapsed into one command line. But what's more interesting, another GEP introduced the ability to include also just-in-time compilation profiles into the cache. No additional flags needed. It just works out of box. And soon we will see some benchmarks for it. But before that, I'd like to mention another performance-related feature. It's related to memory management. And that GP519 about compact object headers. Previously, it was in preview. Now it's finalized. And from that slide, you can see basically what's the difference. And the difference that is that based on practical observations, it was possible to assume that JVM needs far less memory per object, per Java object, to hold all the necessary structures. And that assumption has finally has been successfully validated in JDK 24, and now we are able to use it in production to shrink the JVM memory footprint. Now about the benchmark itself. It evaluated both features we've just discussed. And here I created a small Quarkus REST API that converts JSON to equivalent YAML payloads. And I set some fixed garbage collection and memory settings. Also, I used some out-of-box management factory code to capture the startup time of JVM. And also, I leveraged the Gatling framework to measure the performance and also to generate workload to build the AOT caches themselves. The source code may be found in the link provided on the slide. It's part of my public repository. And some short summary on the results. Here we can see that startup times actually improve with both features. Just AOT itself improves by around 32%. And also, if we add compressed object headers on top, that's another 6%, which is nice. And taking into account that this is a pretty simple application, large-scale production services will benefit from those optimizations even further. And here you can see some graphics from the Gatling test. So after I captured the caches, I ran a comparative 1-minute test with each setup. And here we can see that naturally the JVM application has some startup spike by around, I don't know, 150 maybe milliseconds. With AOT, it's reduced by maybe around 90. And with AOT and compressed object headers, it reduced even further. So the numbers speak for themselves. Now a couple of GAPs about the Java Flight Recorder tool feature, which is about profiling Java applications. And here we have the first feature which improves the profiling itself, the quality of profiling. Because previously, what profilers did without instrumentation, without code interpretation, they had to synchronize with threads of our applications at some save points. That introduced bias. To overcome that bias, GFR was able to make some assumptions, but those assumptions may lead to risks of crashing the JVM itself. And now this feature brings the best of both worlds. So GFR is able to leave asynchronous requests to sample the performance, and the JVM threads serve those requests when it's possible, as soon as it's possible. So less bias and more precise results. And the next GEP introduces 2 additional options for profiling. I'll show an example soon. So basically, you are able to quite easily collect traces for certain method invocations and also collect timing results. So mean, max, average execution times. And this is configured by some simple options, which you can see from this slide. And let's have a look at a simple example. The example was based on this llama3.java project from GitHub. So big cheers to the original author who did an enormous effort of porting some C code to Java. And also, it's interesting that this application leverages the FFM and vector APIs under the hood to run the LLM efficiently. And I run a profiling session to collect a profile. I'll show you one. So I hope I can zoom a little bit. So this is the JDK mission control tool, which is able to read what was recorded with a GFR. And we go to the event browser. Then we filter by method keyword. And here we have, oh, sorry, it's not able to zoom. I'm really sorry who is not able to see it properly. But basically, there is a group called method tracing, and there are two event types, method timing and method trace. So for tracing, I used one annotation. I put it on one of the computationally intensive methods to presume that I want to see who invokes it. And we have 23 calls throughout the profiling session. And then we have some statistics from another annotation, which was put on some parallelization code, namely on two methods for which works with long arrays and int arrays. And here we see that minimum time is this, maximum time is that, and also we have the number of invocations and average time of the method's execution. So pretty convenient. Now let's go back to the presentation. And let's talk a little bit garbage collection. The most noteworthy feature of JDK in terms of garbage collection is that the Shenandoah generational mode is finally production ready. It was experimental in JDK 24. And the idea is to leverage the low pose, quite efficient garbage collection mechanism and adopt it for more variable workloads often seen in microservices. And I ran a synthetic GMH test. I reused the benchmark that I used to review JDK 24. It compares different garbage collection algorithms under synthetic workloads. So those are pretty focused on different low-level operations like memory copying, memory reading, arrays processing, etc. It's not very representative of actual real-world applications, but nevertheless, it's able to highlight some strengths and weaknesses of certain garbage collection implementations. And of course, you may find the source code of the benchmark on GitHub. And now let's not waste too much time, just let's have a look at some results. So as I've already mentioned, there are a couple of disclaimers. First of all, I was forced to do the benchmarks on my office laptop with lots of security software, which probably affected the results. So my laptop was under maintenance. It is what it is. And next, as I've already mentioned, those are synthetic tests which emphasize some low-level operations, and the results will be greatly different for real-life applications. So you need to benchmark it yourself if you want to see what it means for you. But generally, there was no significant change since JDK 24, but nevertheless, there are a couple of outliers. Namely, Shenandoah Generational was able to improve its burst memory allocation performance. It degraded a little bit in tests that emphasize read barriers. So this is a construct related to garbage collection, how it internally works under concurrent workload in JVM. But on the upside, it was able to improve with write barriers and was able to improve its performance significantly with overall heap allocation bandwidth. And if we look at some images, it looks like that. So you may find the full precompiled report from my machine on GitHub if you want to compare it with your own results, just in case. Now let's go to the final section, which is about core API changes. And the first feature here to look at is about stable values API. The problem that is attempted to be solved is about the problem of lazy initialization and efficient initialization. And if we look at final fields in JVM, those support some internal optimizations like constant folding, but nevertheless, all final fields are eagerly initialized. So every time your object is created, every time your class is loaded, all the final fields are initialized eagerly. The alternative previously included class loader idiom, which requires an additional class per field you need to process this way, which is quite clunky and increases memory footprint. Also, we have the old and good or bad, name it whatever you like, double-checked locking, which is tightly coupled with the well-known singleton anti-pattern. And it doesn't benefit from JVM optimizations and looks weird. But another option is functional style like concurrent map compute if absent, but it also has no JVM optimizations, unfortunately. And the stable values API introduces a solution, a separate abstraction, which allows to have the best of both worlds, namely lazy initialization and internal JVM optimizations. And let's have a look at an example. Sorry. The IDE was not able to memorize the last window I opened. So let me zoom a little bit. These are the consequences of the previous API example. Okay. We have, let's suppose we have some sort of observability service which is akin to Logger, SLF for JLogger, but about some statistics. So it allows us to record events. We want to have one such thing per class, like we do with loggers, okay? And here we have a service bin, which does exactly that. So here we have a new construct via the stable value API supplier call, and it provides us with a lazy supplier which computes the service bin when it's needed. And for demonstration purposes, I have one operation which involves invocations to the observability service and another that doesn't have that. Let's have a look at a test. Sorry, not opened here. Okay, so let's run and zoom in. So this is a pretty simple test. It initializes some mocks and expects and is meant to demonstrate what happens under the hood via logging. Let's wait a little bit. Hopefully it will be able to complete in time. We should be able to fit into our time slot, fortunately. So basically, what we do here, we make the invocation which doesn't involve the observability service. Then we do another one which involves the observability service. And then we have another login event to separate what happens. So here we have it. So the first event, the read event get by ID, doesn't touch the observability service. Then we see that when we invoke saving the customer, the observability service is invoked for the first time and the lazy supplier kicks in. So we have the observability service initialized. And then we successfully send the observability event to the observability service. So everything works as expected. Let's get back to the presentation. A couple more features. The next feature set is related to some things that make Java closer to such languages as Python in terms of ability to quickly experiment. And this is about Project Ember. It introduced 3 finalized features and another feature which is still in preview. The first GP allows us to use import statements with which target whole modules. So hopefully you remember what are the Jigsaw modules. Next, GP allows us to use compact source files. So what it means you will see in just a moment, which basically provide a shorthand for more conventional main methods with the whole class associated with it, which presents some sort of boilerplate code when we need to try something small and quick. And the third GP makes it easier to extend constructors when we do inheritance. And namely, this feature allows us to insert some statements before invocation of the super constructor. The full source code may be found on my public GitHub repo, and let's have a look at the example itself. So Project Ember. And here we have a simple project structure. The first part is about some supposedly third-party module. This is a cache abstraction, fixture cache abstraction, and we suppose that it has some heavyweight initialization logic in its constructor. And we want to introduce some validation before we do this initialization. And we want to play with this library without creating a full-blown project. In order to do that, we create just one Java file. We even don't need to compile it, thanks to some relatively recent abilities of JVM to compile things on the fly. And here we have a simplified structure which is about the compact source files. We have just function style main method. We don't need any arguments in this case, so we can omit them. We don't have to make it static as well. As you can see, we import the whole module with the third-party library I've just demonstrated about the cache. And we have some classes underneath. The first one to look at is our custom cache extension, which extends from the third-party cache and introduces some validations before invoking the presumably heavyweight constructor of its parent. And here we look for some weak algorithms in case these are used, we fail immediately. And also we introduce some validations of the cache size itself. The rest is pretty basic. Next, we have a service which wraps the cache. And here we demonstrate the GEP, which is still in preview. So basically, these are some set of syntactical improvements for pattern matching and instance of. And the goal is to make those language features work with primitive types. So now we are able to safely and efficiently validate whether a given broader value may be safely cast down to a smaller data type. And here we benefit from this feature to determine whether we are able to invoke some optimized logic for byte values, and only if necessary, fall back to some more heavyweight implementation. And this is demonstrated with login. And let's run the thing to see it works. Let me zoom. So we go to Project Ember and we run the run bot, which I'll show as well. Sorry. So as you can see, the command line itself here, We just invoke Java with enable preview features because we want to use the enhanced pattern matching on primitive types. Then we add the module, our fictitious third-party library with the cache, some module-related configuration, and then we pass just the Java file itself. We don't need to compile it explicitly. And the logs tell us that when we invoke the service method with a small value which fits in byte, the byte implementation is invoked as expected. And when we invoke with a bigger integer value, the integer version is invoked as expected. So this is what we have with Project Ember recently. Now, the famous Project Loom, which brought virtual threads to us in the past, and now it's still working on some concurrency improvements. The first improvement, which is about scoped values, is finalized, and the structured concurrency itself, unfortunately, will be held down till the next release, I suppose. But there are just minor improvements, so hopefully it will be able to bring us some production benefits quite soon. And let's have a look, an example actually, and recap what is structured concurrency on its own. Project Loom. So here we have, suppose we have some sort of business logic which involves multiple services. So here we have some invoice service which executes several steps in invoice processing. It takes customer ID, order ID, and language. Then it gets the customer data, then the order data, then renders the template using the requested language. And every step, as usual, requires some exception handling, some boilerplate code, which is usual to executor service-based implementations. So basically, we have 1, 2, 3 lines of useful code, 4, 5, 6, 7, and the rest is boilerplate. Not very handful, right? And if we have a look at what a structured concurrency proposes to us, it's much more compact. As you might remember, we have the abstraction of structured task scope, which is some sort of context for managing our forked tasks. It runs on virtual threads by default. It's possible to run on traditional threads, but it's not recommended for obvious reasons, because we might spawn thousands of such tasks, obviously, and overload our platform threads, which is not good. And here we fork each task from the scope, then join. So it's a lot easier than having 3 try-catch statements. Then we get the results and render the final step. Much more compact. Not ideal, but much better. And if we have a look at some scoped value examples, the easiest way to demonstrate that is on some login features. Okay, so we have a tracing static utility which holds a scoped value. So this is the finalized API. And it represents another kind of context. It's a counterpart to the old good thread locals, but much more concise and much more safe in terms of memory leaks, because I believe that every seasoned Java engineer has faced a situation when someone forgets to free thread local, and over time, memory gets accumulated, and boom, we have an out-of-memory error. With scoped values, this is much harder to achieve, because every invocation which actually uses the memory is wrapped in a nice lambda. So here we have our login service, And we attach a string with a trace ID to the scoped value. And then, okay, so let's have a look maybe at the test itself to better understand what's going on. Oh, probably I forgot to add one. Okay, so basically we have a tracing utility. It's invoked from the so it's invoked from the structured invoice service. Sorry, I was in a hurry to fit in the time slot. That's why I forgot. So here we allocate the trace ID itself, put it to pass it to every invocation we have, and what happens under the hood, that trace ID is bound to scoped value and reused nicely for each thread. So this is the example. So this is all about the new features in JDK 25, which is a long-term support release, and thus you may safely migrate to it and use all the features finalized in that release. And since it was quite a long time since the last long-term support release, which is 21, let's recap what JDK 25 long-term release brings us since JDK 21. And first of all, it's about language ergonomics. This is about flexible constructor bodies. I demonstrated that in my project Ember example just a couple of minutes ago. Next, we have some improvements to pattern matching. So this is for efficient data-oriented programming. I believe Oracle has a series of blog posts related to that concept. Then we have compact source files. I demonstrated an example as well. And also we have support for Markdown in Java documentation, which allows us to write some well-formatted comments for our code. Next, we have core API improvements. That's about foreign functions in memory API. This is important for AI because it enables high-performance computing by invoking directly native libraries and using off-heap memory. And this is without the old and unstable abstraction of a Java native interface. Next, we have scoped values. I've just showed them to you. New security APIs. So this is about different format support, new APIs for security key manipulation, etc. Next, we have stream gatherers. So this is the extension to Streams API, which basically allows us to have something similar to collectors, but in the middle of the pipeline. So they are not terminal. You can proceed with further steps of processing. And next, we have class file API, which is a replacement to third-party libraries like ASM or ByteBuddy, and allows us to have more safe bytecode manipulations in such frameworks like Spring Framework or code generation libraries like Lombok, etc. As for JVM itself, we have different improvements to performance in the form of AOT for faster startup, the new generation of Shenandoah garbage collector. I showed a benchmark to you in the middle of the presentation. And we have improvements to profiling with GFR. We've discussed that in this presentation as well. And here you can find some articles that were used during preparation of this presentation. And of course, you may find the links to my public GitHub repository on the previous slides. Thank you very much. Let's go to the questions, if any.
Thank you very much for the presentation. So even with some technical troubles, we were able to finish in time. That's great. Yeah, guys. So you can, as Egan mentioned, you can check repository later and check it by yourself. Yeah, if you weren't able to see it on the screen properly, so please do it later. Okay, so we have a couple questions. First one is related to AOT and JIT caches, and the question is, where are they located? Wondering if it gives any advantages for containerized apps.
So as I've mentioned, let's go back to the slide itself. The AOT processing involves several steps. Previously, you had to run 3 steps, namely collect the list of classes you want to capture. The next step to actually use that configuration to make some sort of warm-up run for your application to collect the metadata required. And that step provides you with an output file, which you can subsequently reuse in the command line arguments of the actual production run, and hopefully boost its startup times and shrink the time till optimal performance. And the next part of the question, please, Ron, could you please repeat?
Yeah, the general question is if this can be anyhow helpful or any advantages for containerized apps.
For containerized apps,
So basically, Docker.
probably. It depends on the complexity of the application. So basically, what we are talking about here is about some workloads which take time to warm up and do some optimizations to the classes, to the bytecode, just-in-time optimization, etc. But in case we are talking about some very lightweight workloads like Lambda functions, for example, in AWS, then probably it doesn't make much sense because the lifetime of such applications is extremely short, and probably the difference between the option with AOT and without will be negligible. But on the other hand, if you load a lot of classes in that Lambda function, which is not advised actually, it may provide some boost to your 99 percentile, for example, in this case.
Okay, thanks for the answer. Guys, we're still waiting for your questions in the chats. We have some time for that. So maybe while we're waiting, a small question from my side. So, as we're speaking about Java 25, which were released in September, in your opinion, when would it be time for to start migration for enterprise project, of course?
Well, I believe it depends on the frameworks and libraries you use on the project because, for example, Spring framework, even in its latest releases, still supports Java 17, if I'm not wrong. So basically, we have quite a lot of time for major migrations. But in case you would like to benefit from the performance optimizations, for example, from JDK 24, JDK 25, it makes sense to consider the effort of migration right now, I believe.
Mm-hmm. Okay. Question from Evgeny. Thank you, Yauhen. Scoped value looks promising. Do you think thread local still have use cases over new API?
Well, from pure functional point of view, they are equivalent. From safety point of view, scoped values are safer, especially in an environment where you use virtual threads, which may spawn in thousands and thousands. Because under the hood, scoped values gracefully deallocate memory associated with them once the virtual thread blocks. But on the other hand, we have a lot of legacy code which relies on thread local libraries. So I'd tell that eventually thread locals might get deprecated, but the legacy code is legacy code. So it's up to the maintainers of that code to migrate to scoped values, which is advisable, I think.
Mm-hmm. Okay. Just me. Let me just pronounce it one more time that GitHub repo will be shared along with presentation. But Ethan, if you can later go to the chat and share the link, would be great. I mean, not now, but maybe after we finish with um, questions. So, guys, if you have any more questions, please feel free to post them into the chat. Yeah, I don't see any right now. So I think we can wrap up on this. Thank you, Ihan, one more time. Great talk. Thank you very much for sharing it with Javon. Thank you for being part of our conference. Yeah, thank you very much.